Okay, now we will systematically derive 7 crystal system and 14 Bravais lattices, etc., based on the repetitiveness of the crystal structures and also based on the symmetry elements. Before doing that, there's one more thing that I wanted to discuss with you. That's the combination of a rotation and the perpendicular translation. I told you several times that crystal structure, the basic principle of crystal structure is repetitiveness, translation vector. That is the basics of crystal structure. And we try to systematically analyze the crystal structures with the symmetry elements in there. So whenever you put symmetry elements in the lattice point, you have to remember that we have to think about these translation vectors. Okay, so let me do this. First of all, let's say if there is a lattice point in here, and there is a lattice point in here with one translation vector, t vectors, in between A and A prime. Now, if I wanted to rotate certain angle, rotation angles alpha of some objects, which is in P1 in here, okay, then this P1 by this alpha rotation operation goes to the P2. But we know the crystal structure, the basic ingredients is the translation vectors. So if there's a translation vector in here, then any objects in P2 should generate the same objects by the same translation vectors. Then this P2 generates P3. Okay, what I'm talking about is just A alpha rotation operation moves P1 pole to P2. Then translation vector moves P2 to P3. Then rotation and translation causes P1 move to P3. So rotation is something that we want to put in the lattice point, symmetries. But we remember that there is a translation vectors. So what kinds of rotation operation we do, we have to think about that rotation and translation should generate another one. So this rotation and translation moves P1 to P3. So in these diagrams, if we draw the lines in here, then this P1 goes to the P3 by the rotation and translation is the same that we find out if there is any rotation operation in here, then this is the angle alpha is the same as one rotation operation at certain point B. And this B can be analyzed geometrically that this is t vector magnitude over t half, then this length is defined by half t vector magnitude cotangent alpha over 2. Okay, so this angle is alpha over 2. So what it means is any rotation operation and translation is the same as one rotation operation at the point of B, and this point of B is expressed in here, lies on the bisector of AA prime, bisector of these vectors, and the distance from this point to B is expressed by this. So rotation and translation generate the same rotation at point B, which is the bisector of the translation vectors, and the distance from the bisector lines to that B point is defined by half over t vector magnitude and cotangent alpha over 2. Okay, so rotation and translation generate the same rotation element at B. Okay, based on that, now we think about the general principles. Now, general principle is when we have lattice points and lattice points and lattice points and lattice point, we define T1 vector and T2 vector. And this is how we define the plane net. But if we put any symmetry elements in here, either 2-fold, 3-fold, 4-fold, 6-fold, then we can define the relationship between T1 vector and T2 vectors in respect to the plane net. Okay? Then that's the plane net that we develop. But we have to think about that if I put certain symmetry elements in here, then with respect to these translation vectors, which is generated in the plane net, what kinds of extra symmetry is developed? That's something that we have to think about. For instance, this is the case where we define lattice point in here, lattice point in here, lattice point in here, lattice point in here. Now we put 2-fold symmetry here. Lattice point has now 2-fold symmetry. And in the plane net, we know that this is the T1 vector and this is T2 vector. In the plane net, based on 2-fold symmetry, T1 vector magnitude is not the same as T2 vector magnitude. Now this angle alpha is in general. Okay, that's what we discussed already. But now, when we think that there is 2-fold symmetry in the lattice point and in the plane net with 2 different translation vectors, what kinds of extra symmetry is developed? Because I have to do this 2-fold rotation operation, backpass 180-degree rotation operation, and translation. Whether it generates another symmetry or not, based on the principles that we discussed in the previous slides. Okay, so it means that when we have 2-fold symmetry at each lattice points, then we have to think about these translation vectors. Then another 2-fold is generated along these lines. Okay, so this is generated bisector lines. Now, if we think about this position, how much of the B point is separate from this bisector point, then this is 0. So 2-fold is just designates and here, here, and here, and here. So finally, if I draw the symmetry elements based on 2-fold plane net, then symmetry elements is expressed like this. Remember that the lattice point only locates here and here and here and here, and the lattice point has 2-fold symmetry. This 2-fold symmetry is just generated there. There is no lattice point. It's just generated there. So if I put any poles, for instance, if I put the pole in here based on 2-fold, then this 2-fold generates poles in here. And since all the lattice points should be identical, then all the poles should be there and there and there. And I put the poles, I put the general poles based on lattice point definition. All the lattice points should be identical in the sense of physics and physical and chemistry wise. Now this one has 2-fold symmetries. So I put the poles like this. Now you can notice immediately that when you put the poles in here, indeed, there's 2-fold generates here, and there's 2-fold generates here. Okay, so these are 2-fold generates here and 2-fold generates here. So these are the generated symmetry elements because we have to think about rotation and translation. 3-fold symmetry, plane net, is the same thing. I put the lattice point in here. And this is T1 vector. Now this is T2 vector. And based on 3-fold symmetry, this one is 120 degree. And this is the plane net. You put the lattice point in the planes. Okay. Then now when you put the 3-fold symmetry in here, then we have to think about threefold and translation. Now, this threefold and translation, which makes the A point move to here, is the same as the translation on the bisector lines, and there is the point in here. You rotate 120 degree, then it just moves to here and here. So there is threefold symmetry at this point. And again, if you put 240 degree rotation and translation, meaning that there is 240 degree rotation at this point, which is the same as this point. So all this B position and C position has extra threefold symmetry elements. Okay, if you want to confirm it, when I draw it like this is the lattice point, and this is T1 vector, this is T2 vector, but this one has now in this case 60 degree rotation angles. If I put threefold, 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 if I put the poles around here, general poles around here, identical to each lattice points. This is the operation that you have to do based on lattice point definition and based on rotational symmetry. Now you see immediately that there is threefold rotation in here. Okay? Threefold rotation, and there is threefold rotation in here. Symmetry elements is here, so there is threefold developed. So these are developed symmetry elements based on rotation and translation. Fourfold symmetry, by the same token, I have 90 degree, A has put 90 degree, fourfold symmetry in here, has the 90 degree, 180, 270 degree rotation, and of course 360 degree rotation. And now you do the translation, you do the translation, you do the translations, you do the translations, and you find out another 90 degree rotation generates where? Another 180 degree rotation generates where? Okay, if you do it, you do the rotation and translation, meaning that there is 90 degree rotation elements at this B1 point. So B1 has fourfold symmetry elements. If you do the 180 degree rotation and translation, has the point in here, because the rotation angle is 180. So B2 has twofold symmetry elements in there, and 270 degree rotation and rotation here, then this point has the 270 degree rotation elements. And this point is the same as this point. So this point has 90 degree and 270 degree rotation elements, which means that has fourfold symmetry. But along the bisector lines of this translation vector, it only has twofold symmetry elements in there. Again, when you put fourfold general pole along each lattice point, you can find out that these extra symmetries indeed can be developed. So these are the symmetry elements. The lattice point is here, 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 here. And the lattice point has fourfold. These fourfold, these twofold, those are all the generated symmetry elements due to the rotation and translation. Okay. These are sixfold plane net. Again, there is a lattice point, there is a lattice point, there is a lattice point, there is a lattice point. For each rotation angles of 60 degree, 120 degree, 180 degree, then you do the translation and you find out where the extra symmetries are developed. Then you find out that this position develops again threefold symmetry elements, and now the bisector lines of each translation vector has twofold symmetry elements. Okay, these are different between 3-fold symmetry and 6-fold symmetry. In the 3-fold symmetry, there's no 2-fold symmetry developed at this bisector lines. Okay. Now, in the case of a mirror plane, we have to also think about mirror and the translation. Mirror and translation perpendicular to the mirror plane. Okay. In the case of mirror plane, when we have lattice point in here, if we put another lattice point in here, then of course this is the translation vector. So we have to have another lattice point in here with the translation vectors. And in the case of mirror plane, there is another way that we put the mirror plane. The mirror plane can be put in between this another lattice point. The mirror plane can be put in between the lattice points. So these are the translation vectors, but now we put the mirror plane in between the lattice points. There are two sets where we can put the mirror planes. So one type is this one, and we put the lattice points in here so that the mirror plane goes in here, and the mirror plane goes in here. And in this case, this one is, we put the mirror plane in here, and basically it's the same thing. It's the same thing. But another set that we can put is the lattice point is here, as we told you in this case. But another set of lattice point is put in between the mirror plane. So one set is in the mirror plane, and one set is in between the mirror plane. There is another set that we can put this lattice point with respect to the mirror planes. Based on that, there are two different plane nets that we can develop. One is we put the mirror plane, let's put the lattice point in here, but the mirror plane is located like this. Right? Then these are the translation vector perpendicular to mirror plane. So mirror operation and translation perpendicular to mirror plane. Then it generates extra mirror plane in between the mirror planes. So these are the mirror plane we put it in the lattice points. Then we will find out that extra mirror plane is generated in between the translation vectors. Why? Let me show you this. So let me put any objects in here. Then the mirror plane generates another objects, A prime. Then of course this is A prime. Okay, so I put the mirror plane operation in here as a general pole, and I put the same general pole for each lattice point. Then we will see that immediately that there is a mirror plane in here, because this A prime, A, this is mirror. Okay, so mirror and the perpendicular translation generates another mirror at half of the translation vectors. This is extra symmetry that is developed. Okay, if I put the mirror in here, perpendicular to each other, then of course the mirror is developed in here. So this is one set of plane net that we'll discuss. This is based on mirror plane, and this is rectangular shape. Another set is that we put the mirror plane in here. These are the lattice points. But mirror plane is here and mirror plane is here, like this. Then we put another lattice point in here, in between. Then, as you see, because the lattice point should be all the same. If there is a lattice point, then this one should be mirror plane also. Okay, so these are the mirror and these are the mirrors. Now, in this case, we put the unit cells like this as a rhombus type. This is what we call diamond rhombus type. And if we put two mirror plane perpendicular each other, M1, M2 perpendicular each other, then when the two mirror plane bisect each other, the twofold is developed, which I will explain to you later. And then this twofold generated, then it also generate another twofold in here, another twofold in here. But in this case, just think about how we developed the rectangular shape and how we developed diamond rhombus type. In this case, lattice point locates in here, here, and here. Okay. So the mirror plane penetrate along the lattice points, and then unit cell is defined like this, which is diamond rhombus type. So the plane net that we discussed has parallelogram, which we put as P, that's consistent with the plane symmetry of one-fold and two-fold. Parallelogram is just anything like this with one-fold symmetry and two-fold symmetry. T1 vector, T2 vector can have any arbitrary numbers, and angle alpha can have any arbitrary numbers. That's what we call parallelogram in the plane net. And we developed 120-degree rhombus based on 3-fold and 6-fold. Forget about this mirror plane yet. That's 120-degree rhombus. Now we developed the square based on 4-fold. Now we developed the rectangular type and diamond rhombus type based on this mirror plane operations. Those are only 5 different types of plane nets that we'll discuss. Symmetry-wise, one-fold parallelogram. Again, lattice point is in here. There's just one-fold symmetry. And the same parallelogram, two-fold symmetry. Lattice point is here, 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 here. With the T1 vector, T2 vector with any arbitrary numbers, and angle alpha, any arbitrary numbers. But when you have two-fold, when the lattice point has two-fold symmetry, you have to find out that extra two-fold is developed here. That's the symmetry elements of plane net based on two-fold. Three-fold, we discussed this one. Now T1 vector, T2 vector has the same magnitude, and this one should have 120 degree. This is lattice point, locates here, and lattice point has three-fold symmetry. Now you find out that extra three-fold is developed there because of rotation and translation. Based on six-fold, the same thing is 120-degree rhombus, but now lattice point has six-fold symmetry elements. In this case, three-fold is developed in here, and two-fold is developed along each bisector lines of translation vectors. Square, I discussed about this. There's a lattice point based on four-fold symmetry. T1 vector, T2 vector should be the same magnitude, and this angle should be 90 degree. And in this case, four-fold is developed and two-fold is developed. But remember, the symmetry is developed, but symmetry is not resulted from the lattice point. Okay, only these are the position where the lattice point locates. And the rectangular type based on the mirror plane, and the mirror plane rhombus type. And in this case, lattice points locates here and here and here. And in this case, lattice points locates here. Then we define this as the unit plane net of diamond. Okay, so there are 5 different plane lattice type, and the symmetry elements that is available for this plane net. And what kinds of symmetry are generated in this plane net is the basis that we derive about 7 crystal system and 14 Bravell lattice in the next lectures. Okay, I'll finish my lecture of this section to here. Okay, thank you very much. Bye now.